Hello everyone, in this video we are going to discuss about a theorem called pumping lemma. So that theorem is used to prove whether it is used to prove the language is not regular. So we know what is mean by regular language. Regular language means a language accepted by finite automata is called as regular language. But if we see some examples, like for every problem we can draw the finite automata so that we can say every language is regular language. But we have some languages which are not regular. So that means like if I take one or two examples like string acceptance, I can say that that language is regular. But at some point, that language will become not regular. So maybe we may able to draw the finite automata, but it may be a non-regular language. So that use like to prove that we are using this pumping lemma. So actually it is a negative theorem. Like that means whatever the language you take, okay, whatever the language you take, maximum it will prove that the language is not regular. So that means every language at some point, by because all the languages you're taking as infinite languages, right? So we will take hardly 10 examples or 20 examples or maximum 100 examples, but more than that 100 we don't consider, like we don't check that all the strings are accepted by the finite automata or not, right? So at some point that language may become not regular, so that can be proved using this pumping lemma theorem. Of course, whatever you take the question, obviously that will be non-regular only if you use pumping lemma theorem, because it is a negative theorem only. So after this session, you can understand what is pumping lemma theorem and how to prove the language is not regular using pumping lemma. And we can see the applications where we are using this pumping lemma theorem. Right. The first one is pumping lemma theorem. So what it is? Actually, it is a basic theorem which is used for checking whether the given string is accepted by regular expression or not. So that actually we can do directly, but why we are going with pumping lemma? So one theme is that any language for which it is possible to design the finite automata, definitely the regular language that we know already, right? So for any language, if we can draw the finite automata, means that is nothing but it's a regular language. Now, what is the pumping lemma theorem? So in this theorem, let L be a regular language. Consider a language L be a regular language. There exists a constant n, such that every string W in L, so sorry, this is Z. Every string Z in L, okay? Every string we are taking as Z. So now length of Z is greater than or equal to n. So what is this constant n? You should take n value as greater than, less than or equal to length of the string. For example, if you take any string like B, so what is the length of the string? Length of the string is 5. So you need to take n value as 5 or less than 5. Okay. So that in that way you need to consider one constant value n. So now break your string into three parts. So what is your string? Your string is Z. Break that string into three parts, U, V, W, such that length of V is greater than or equal to 1. Length of V is greater than or equal to 1. And length of UV, so combined strings UV, length of UV is less than or equal to N. So we need to check all these things for each example. For example, if I consider a string uh, like this. So what is the length of the string? N value is 6. So most of the cases consider n value as same as your length of the string. So n value I am taking as 6. Now consider UVW. So we need to divide our string into three parts where V value, length of V should be greater than or equal to 1. So what I'm doing? So I'm taking this value as V and this value as U and this value as W, U, V, W, U, V, W. So you can divide your string in any fashion, any case, but it should satisfy these conditions. What is the length of V? Length of V is V is AB. So length of AB is 2. It is greater than or equal to 1. So this condition is satisfied. Next, length of UV. So UV. So what is the length of UV? So we have 4 letters here. The length is 4, which is less than or equal to n only, right? So it should satisfy these two conditions. So like this, you need to divide your string into three parts, U, V, W. For all I is greater than or equal to 0, the string x power I, Z is also in N. So what we are taking, so this is not x, y, z, it is u, v, w, right? So u, v power I, w, u, v power I, w. So now what is u, v, w? U, v, w is triple A, triple. Now consider I value, increase I value. So UVW value is triple A, triple B. Now consider I value. So I value I'm increasing. So UV power I W. So consider I value as 0. Then V power 0 W. What you will get? V power 0 in the sense 1, right? So you will get UW. So what is UW more? So UW is double A, double B. Double A, double B. So you need to check whether this string is available in your language or not. If it is available, go with the next one. So what is the next one? Substitute I value as 1. I value 1 in the sense you will get UVW. What is UVW? Triple A, triple B. So anyhow, this will be available in your language. Now I value is 2. V square W. That means U value is as it is. V value you need to write it for 2 times. That means AB 1 time, AB 2 times. Next followed by W value, that is B. So I need to check whether this string is available in your language or not. If even it is also available in your language, then go with the next one. So like that, you need to repeat this process. At some point, whatever the string you are getting, that will not be available in your language. Here only we can stop. See here, whatever the language I'm taking, A is followed by base. But if you observe here, A is followed by base. After that, immediately you're getting A. That means this string will not be available in your language. If the string is not available in your language, then you can say your language is not regular. Not regular. Okay. So it should satisfy this condition. U, V power I, W should also be available in L. Then in that case, I can call that language as regular. Otherwise, it is not regular. But for every problem, for any problem, at some point, this condition will fail. So obviously, you can say that the language is not regular. So generally, you'll get the some questions like they will give some question language. N is a prime number something, prove this language as not regular, or just check whether this language is regular or not regular using pumping lemma. So even if you don't know the answer, just write the answer L is not regular. That's it. Why? Because using pumping lemma, you can prove any language as not regular only. Why? Because at some point, every language will become not regular. So infinite thing, we cannot calculate everything, right? We cannot point out everything. So at some point, at certain point, every language will become not regular only. Even if you don't know the answer, you can simply write that statement, you will get the marks. I mean, not complete marks, at least 1 mark you'll get for that. So this is the question. And coming to proof, I'm just taking a DFA here. So with a pi tuple notation, then I'm taking a transition here. So Q0, Q1, Q2, and so on Qi, where it is reaching to final state, that is Qi. Now, so consider this diagram. This is the diagram. See here Q0 and so on. It is reaching to some intermediate state, and so on. Again, it is reaching to final state. So when I can say the given string is accepted by this finite automata, it should start the process from Q0 and it should reach the final state Qm. In that case, I can accept that string. I can consider the string in the language, right? So now, what you are doing here, in between this, you are repeating something. You are repeating self loop, right? That means that's what we are doing here. UVW, this thing, this between thing, like whatever the thing you're getting in the middle, that you're repeating for number of times. You're pumping and pumping. Like the pumping will be like will not be stopped at all. Okay, pumping in the sense pushing or giving. Okay, so the V value, every time you will provide multiple values for V, and every value should be accepted by that finite automata. If it is accepted, then it can reach to final state. If it is not accepted, it will be stopped here itself. That will not be reached to final state. That means that will not be accepted, right? So whatever the thing you are looping here, self looping, that is nothing but the V power I you are doing. Okay, so if it is available in your language, all the possibilities are available in your language, then I can call your language as regular language. See here, that is why we have proved is given any long string can be accepted by finite automata. we should be able to find a substring near the beginning with the string that may be pumped. That means repeated as many times as we like. So we should repeat a substring as many times as we want. Okay. So even that it is accepted by the finite language, then I can say that the language is regular language. So that is about pumping lemma. So here we don't have anything, we are not proving anything. Okay. So if u v power I w is belongs to your L, then I can call your L as regular language. That is the main important point here, right? So now this topic is, so next one is the pumping lemma is used to check whether the given language is regular or not, right? For that purpose only we are using pumping lemma. Then pumping lemma is a negative test. It can be used in applications like showing an invalid move in game of chess, right? So in chess, while playing, like we'll check every move, whether this move is correct or not, whether this move is correct or not, right? So for example, like some points are there, like that can be moved to only limited steps. So if I take that. Soldier, it can move only single step, right? So what happens if I go to the next step, or if I take two steps ahead, and what happens, right? So at some case, at some point, that will become fail, that will be failed, right? To prove that failureness, we are using this pumping lemma. See, if you observe here, it is a negative test. It is a negative test. Only to check that negative cases, you are going to use this pumping lemma. Okay. So next, applications of pumping lemma. So where we use this pumping lemma in the real world. So as we discussed in the previous slide, so it is used to invalid move, like identify the invalid move in chess, right? So whether that move is valid or invalid, to check that, we're going to use this pumping lemma in that chess game. So obviously, while playing, like if we play physically, we don't use this theorem, but in the mobile application or in the internet, we can play the chess, right? So in that, internally while writing that logic, they will use this theorem. Okay. Right. The main application of pumping lemma is to prove that the language is not regular. See here, that certain languages are not regular. To prove this, the language is not regular, we are using this pumping lemma. And coming to another application, it is used to determining the cutoff temperatures. Cutoff temperatures. Generally, we say like high voltage, low voltage, right? So, what is the meaning of that high voltage? So, whenever you get high voltage, like there will be a blast, right? So that means there will be a point cutoff for your temperature that will be calculated using this pumping lemma only. So first you will increase by 1 unit, 1, 2, then 3 units, 4 units, 5 units, and so on till what you are increasing that till the like thing will blast, right? So whenever the thing is going to blast, that temperature will be considered as cutoff temperature. To calculate that, we are using this pumping lemma. So these are the applications of pumping lemma, and we have some problems here. So the first thing is show that L is equal to B power I square, where I is greater than 1 is not regular. So first try to write the language, okay? Try to write the language. So we will take the language, okay? We'll take one empty slide, then we'll try to solve this. So L is equal to B power I square. So L is equal to B power I squared, where I is greater than 1. So we'll write the language first. If I value is the minimum value for I is 2, I is greater than 1. So 2 square means 4, B power 4. B power 4 means 4 base you need to get. Then 3 square. 3 square means 9. So 9 base you should write. 6 base, 9 base, and so on. So consider any string here. Okay, consider any string. So this is very lengthy string. I'll take this. 6, 9 base, right? 6, 9 base. So now divide this into 3 parts. U, V, W, where what is n value for this one? So n value for this I'm taking as 9. Why? Because the length of the string is 9. So I'm taking n value is also 9. Now divide your string into 3 parts such that V should be greater than or equal to 1 and length of UV should be less than or equal to n. So V value I'm taking as this value as V, this as U, and this as W. Okay, U, V, W. Now check length of V is 2. Is greater than or equal to 1. It is satisfying. Length of UV. So what is the length of UV? It is 5. Is less than or equal to 9. It is also satisfying. Right? So now we'll check U, V power I, W. Consider I value as 0. So if I substitute I value as 0, what you will get, ma? UW. What is UW? How many B's you will get? U followed by W. So U is 3 B's, W is 7 B's. So do I get 7 B's in my language? Do I get 7 B's in my language? See here 4 B's, it is starting with 4 B's. The next one is 9 B's. In between this we don't have any strings. That means 7 B's string is not belongs to your language. So if you are not like okay with this, then you can go with the next case. Obviously it is not related to your language. That here itself you can stop the process and you can tell L is not a regular language. You can take one more case, I is equal to 1. If I take I value as 1, so V power I, U, V, W. What is U, V, W? As it is, the given string only, right? So 9 B's, 3, 6, 7, 8, 9. So 9 B's are available in your language. So this string belongs to language. Next, I value is 2. I value is 2 in the sense V square W. So V, you need to write it for 2 times. U as it is, triple B. V is 2 B's, you need to write it for 2 times. Then W is 4 B's. How many B's we are getting? 3, 6, 9, 11. So check whether 11 B's are available in your language or not. After 9, what you will get? 3 square is over. Next to 4 square, right? 4 square means 16. You will get next one is 16 B's. That means 11 B's is not belongs to L. That means directly you can say L is not regular. So if you get all these conditions as true, if the first one is belongs to L, second one belongs to L, third one is also belongs to L, then you can say L is regular. So you need to check this process. You need to continue this process till you get a string which doesn't belongs to that language. Why? Because pumping lemma is a negative theorem. At certain point, definitely you will get a string which does not belongs to your language. So there you need to stop the process. But for this problem, in the first case itself, the condition failed. So you can say the L is not regular in the first case itself. So remaining everything, all the problems are similar, no? So I hope everyone is clear with this. So next one is a power p, where p is a prime number. So here only we'll discuss a power p, where p is a prime number. So L is equal to a power p, where p is a prime number. So what are the prime numbers? We have 2, 3, 5, 7, 11, and so on. That means a square, 2 is a cube, 3 is a power 5, 5 is and a power 7, 7 is, and so on. Consider any string. I'm taking this 5 length string. So we need to divide the string into 3 parts, right? U, V, W. So better you take more length string, okay? The string with more length. 5 is, this is Z, and now what is n value? Length of the string, right? That is 5. Length of the string I'm taking it as 5. Now then consider, divide your string into 3 parts, U, V, W, where length of V should be greater than or equal to 1 and length of UV is less than or equal to N. So I'm taking this as V, this as U, and this as W. Now we will check length of V is 2, which is greater than or equal to 1, and length of UV is 3, which is less than or equal to 5. So both conditions are satisfied. See, for every problem, you need to check all these conditions now. Whatever the values you are taking, they should satisfy all these conditions. Now, first you need to check U, V power I, W. So if I is equal to 0, we will get UW. What is UW value? U value is single A, W value is 2 A's. So 3 A's, yes, 3 A's are available in string. So this is belongs to L. 3 A's will belongs to L. Next, I is equal to 1. If I take I value as 1, what you will get? U, V, W. What is UVW? It is 5 A's also which belongs to M. Satisfied. Next I value is 2. That means U V square W. Then U value is single A, V value is double A. That means you need to write it for 2 times. Why? Because V square. Then W value is again 2 A's. How many A's you are getting? 7 A's. Yes, 7 A's is available in our language. This also belongs to A. See, it seems like what we feel, it is a regular language. Why? Because 3 conditions are true, right? Now, we'll check what the next value. I is equal to 3. V cube 3, W. That means single A for U. V means double A. You need to write it for 3 times. 1, 2, 3. W means 2 A's. How many A's you are getting? Totally 9 A's you are getting. 9 A's are not available in your language, which doesn't belongs to M. This condition is failed, then you can say L is not regular. See, if you observe here at some point, for some problems we may get a failure case at I is equal to 50 also. At I is equal to 50 also. Okay. So at some point, every language will become non-regular. So to prove that, only we are using pumping lemma theorem. So this is over, and next problem, zeros followed by ones. So 0 per n, 1 per n plus 1. So where n is greater than 0 is not regular. See, in the question itself they'll say. So to prove that the language is not regular. So if they ask to prove it as regular or not regular, you should use pumping lemma. Even if they don't mention in the question use pumping lemma, you need to use the pumping lemma theorem. So, and these are the homework problems. Just try to practice these problems. I hope everyone is clear with this session. Thank you.